known. In the last part of this reading group or course, we talked about images and the various issues in images, and they started to talk about depth images. So I'll start to get from the point which is depth images for this lecture, and see how we can proceed with this kind of with this issue. So first of all, when we talk about the acquisition of depth images, we talk pretty much about three major technologies. One, which is the stereo illumination, and the structured lighting, and 3D laser scanner. The first one, which is pretty much the initial technology which people try to estimate the depth of the image based on various techniques to try to recover the depth from the shading information. Pretty much most of these technology were based on trying to illuminate the object in from specific point, take an image, and then illuminate from different point, take another image, and try to kind of find correspondence between these points. Most of these technology assume the position of the light is known, the position of the camera is known, and the scene is fixed or static, it doesn't move. For that, it was possible to find the match between point and then triangulate to recover the depth image. Maybe the triangulation, I'll go later in the course about this, but it's pretty much technique to be able to recover the depth of a point based on two or more images. The more common or more accurate in trying to capture actually a lot of most of the market recently is the structured light for 3D. The structured light, pretty much the aim of the structured light to illuminate the object with the light structure, pretty much like a filter you often can put in kind of in a light source, and it will project on the object, and it deform based on the distance from of the object or the position from the lighting source. And the purpose of this lighting structure is to be able to correspond between the images of this object from different position. Because, for example, if we look at this object, pretty much very hard to find a salience point that you can correspond from different images, because most of these places are pretty much similar. Now, if we illuminate this with a kind of structured light, we can use this structured light as we see in the first, the second, and the third images in order to correspond between the images, and then we can recover the depth. Pretty much Kinect is based on similar technology, which is what it's doing is projecting circles on the viewed scene, and when you get this, the size of this circles varies according to their distance from the camera. One thing which is you need to determine, the simple thing is which pixels belong to which circle in the image. The moment you know the circle, you can determine its size or approximate its size, and based on that, you can estimate its depth. For that reason, the depth resolution is not that accurate or not really kind of high, because exactly the ability to determine to which circle this pixel belongs. This is one issue. The second issue, because usually in order not to interfere the structured light with the RGB image, with Kinect and like similar technique, which is trying kind of to use different lighting. So most of these cameras use infrared, and in order to not to interfere with the RGB camera, and for that, most of these technologies, almost all of these technologies, which is based on infrared, doesn't work outside. They work indoors and they don't work outside. So this is pretty much the issue of using the structured light. When we will talk about like a correspondence and matches for these images to reconstruct the depth images, we will go deep into these issues. So it's not really the aim of this part. Later we will go in detail about this. Why it's not moving? So the other issue, which is based on laser scanner, the initial technology of the laser scanners tried to get pretty much scanning small statues and toys. And the idea will get stage, and the stage will rotate around an axis in fixed speed. And then you have one laser beam that will go like up also in fixed like speed or fixed time. So each time the stage will rotate 360 degrees, it's pretty much actually encounter or register one contour of this object. Then the laser scans move a little bit up the laser beam, and it's again register or like kind of encounter another like contour and so on. So pretty much you get kind of contours of this object, which is you will be able to recover the entire model. Now, one thing which is about the laser beam is the technologies meant that you get the distance based on the difference on the returning or the returning light of the laser beam. And this is how you evaluate the distance. It's pretty much accurate and actually could also work very easy. The only difference is the beam, what you can scan pretty much like any other camera, what you see the first hit of the beam. So if you have kind of like cavities which are not clear to the beam, it's not easy, or you need to change the position of the beam in order to scan it. Laser, later like the technology was more extended into kind of not one beam or like kind of ability to scan in more automatic like indoors pretty much. Most of these technologies use mirrors and prism in order to spread the beam and change direction. So one of the technology, which is not this one, pretty much this is have an array of laser beams. The other technologies were based on pretty much you have a kind of one beam which is fixed, and then you have a rotated mirror. So pretty much the beam will hit the mirror and then will hit the scanned position. And what will happen, this mirror will rotate, which will enable kind of creating a circle of like scanned point. And then the mirror will change its angle and scan another like another kind of contour. And so on. It's pretty much getting contour. That camera or that scanner enables scanning indoors. Pretty much similar technology, but instead of scanning with one beam, the beam can actually rotate inside the room and scan a room. This is the idea. Most of these scans were used for kind of reverse engineering in car mechanics, or kind of checking kind of the validity of manufactured object in mechanical industry. Later, this technology get actually more spread out and enable scanning cities and outdoors. The things here, you need more power in order to get strong laser beam and to enable you to scan points from far away. It works outside, it works during the night, doesn't really matter. The only limitation that it's the black color absorb the beam, which does not allow scanning black object. For pretty much you can scan everything, and you can scan most of these scans usually done at night in order to be able to scan the object without kind of interfering or moving object in the way. So this is the kind of scanner which you will get, and it's pretty much often like installed in the top of the car, which is enable like the scanning 360 degrees around the car. The aim of most of these technologies and projects to be able to scan cities and their most of these projects trying kind of to create what they call a virtual city that aims to replace what we see now as Google Street. You will get 3D dimension of the object with texture and with images, and there is a lot of works going to do that. These are some of the examples which were used or like creating by this vehicle to scanning these streets. And what you see the trees. Some project actually trying also to recover the trees of the structure. So what we will get in this eventually from all these technologies, and we will get a point cloud, or the simple part of this, we will get what we call the depth image. A depth image is different from a point cloud point cloud is a pretty much scattered point in the space, in the 3D space. And depth image is what we assume it's received from one image, which pretty much what we will get. This is the image we will get. This is the depth, which is will be recorded. So we have for each pixel in the image, we record its depth. Instead of usually we record the color or the intensity, here we record the depth. So this is pretty much how the image will look like. So we have, it's pretty much perceived as a grayscale image, where the gray value determine the depth. Could be 1 byte, 2 byte, whatever actually the initial information you get. So this is one kind of depth images. The big problem, or like the issues, is about the depth. It's supposed to resemble a surface. And resembling a surface, it's very important to know what kind of information in addition to the depth. The first thing, normal. The first thing which will come to mind is to try, in order to be able to recover the structure of this surface, we need a normal. Now, the camera will get us a point, and this point pretty much only the depth, and not necessarily the depth of the camera. It could be normalized with respect to kind of some position. But for us, it's this is the depth value. Now we need to estimate the normal. Now, estimating the normal could be by one of the issues, which is some devices may give us the normal on these as part of the depth images, which is very rare that the device will give us the normal of the depth images. But if it's not there, it's very important to estimate it. So we need to compute the normal somehow. So one thing which is, if we need to compute the normal, we need to look where we can get the information about computing the normal. Neighbors. This is the only information we have is the neighbors, is about their neighbors. So what kind of technique we can get? If we have a point, we assume we will have a k neighbors. We can compute this using KD3 or whatever technique, and we get the kind of a neighborhood of a point. Now let us call it a neighborhood of a point. Now, one of the things which is one of the things which is, what's the size of this neighborhood? What? What's this is? What's is how we 1 meter, 2 meter, 1 kilometer? How many? What?
With research and with half research.
Within, it's kind of let us assume maybe the kind of the size as a radius is not really the kind of the things which is we are looking for, because it depends on the distribution and the density of the scanning. So if we have the points, we will have maybe 1 or 2, or let us look at the nearest k points. And again, how we determine this k?
Based on the accreditation of the device. Relative to, based on the accreditation of the device.
What information in the device will give you this k?
The camera intrinsic parameters?
you don't know them when you get the depth images. Someone give you depth images, you don't know this is, forget about now anything from the camera. You get the depth images and that's it.
Do you choose it?
We choose it now based on what? This is really the issue which is important. One thing, let us start with, if I have a point, and now how many points around it will be at least enough? 1 point to determine the normal, definitely it's impossible, yes? Because what I will get a line that will not be able to determine the point, yes? Now, this is one thing which is, so at least I need 2 points in order to determine the normal. Now, the one thing which is maybe from the Euler theorem, we know that if this is a planar graph, we will have something like 6 neighbors. So this is pretty much, we assume the minimum, like this is, if we think about this, at least if this is a planar graph. But the number that should be high. If they are too small, we cannot really determine accurately the normal. If they are too big, we will have influence from far away. Pretty much it's an ad hoc. We cannot know. There is some, like we could maybe see later in optimization techniques on how, what's the size of the neighborhood which is provide the best estimate of the normal. Because if it's far away, let us assume we want, this is the original surface. And this is what I want, this is the normal you would like to estimate. So if we have a neighborhood that will maybe this size, it will give us pretty much good estimate. If we have a neighborhood of this size, it's too big. Now, or like if we take like something like, it's too big, and it's pretty much will not give us the accurate number. So it's like you should not take minimum than 6 points, definitely. You should take something which is large number. Again, depends of the density. If you know that the density is high, you would maybe take like small neighborhood, but again, it should be derived by the number of points. Now, let us assume we already say we know what's the neighborhood. And we say, okay, we'll get k points that determine the neighborhood. Now, how we will estimate the normal of this point? We get k points around this point, scattered somehow randomly, we don't know. Now we need to estimate the normal.
The average normal based on 3 points.
We could actually, okay, go ahead.
Yeah, you pick 3 points, compute the normal, and do the same thing for the points, and do the average of the normal. I don't know.
Yeah, this is maybe will be the simplest. We'll go over it and see. This is one thing. It's take kind of the points around this. Try to kind of resemble generated triangles, which is you think could be a triangle in this surface, and then estimate the normal based on this kind of like assumption. So this is one approach. The second approach,
We try to calculate the plane, a plane that match more or less the distance between the point and the plane is the minimum, and then calculate the normal of the plane.
yeah, this is another definitely valid technique, which is we called fitting a plan. So we have now k points. You fit the plan in k points while minimizing the square of the difference between them. And the normal of this plan will be pretty much the normal you are like looking for. This is the third technique, or like this is a technique which is, I'll go in depth on these things.
possible to calculate not the plane but the surface that match, like maybe like instead of plane maybe like surface and then average a little bit the normal.
So it's the same like regression, but instead of a plane, like a surface.
Yes.
Like maybe add the degree of the
That will be complicated because then you need to kind of like compute the derivative, the gradient of the plane at that specific point, and then based on that you compute. So pretty much, it's better to stick with the plane. And this is the other issue, which will be based on like eigenvalues and eigenvectors. So if you, I assume everyone knows what's an eigenvalue and what's an eigenvector. Okay, so I'll go and like over these, like, and if someone have any question, I'll be happy like to answer. One simple technique, if we have this is the neighboring point that we want to compute the normal, we will assume that these points will determine the normal based on these points. Now, if we just recall some of the little thing, if we have a triangle, and this triangle ABC, we could compute the normal of the triangle very simply, just like computing this vector u, this vector v, and then taking, should be cross product, not dot product. So the cross product of the two vectors, then we normalize, we get the normal. Is that clear for everybody? Does anyone like know how to compute the cross product or needs? Don't hesitate to ask. It's like we all study this, and we often, if we don't use them, we just miss them. The cross product, should be not the dot, should be the cross product. This is a mistake. So the cross product pretty much what will give us the normal to these two. And it's easy to compute. Just if we look at this, like if someone just kind of if I have two vectors u, which will be, let us call it x u, y u, v z u, and the other vector will be v, so it should be x v, y v, and z v. I usually take very simple approach to compute the cross product. So I started with I, j, k, the unit vectors. Then I write x, u, y, u, v, and z, u, and then x, v, y, v, and z, v. And then pretty much I compute the determinant of these vectors. This will lead to a vector which is pretty much will be I multiplied by some term here, and then j multiplied by another term, and k, should be plus. And k multiplied by another term. This will be the x component, and this will be the y component, this will be the z component. So this is normal will be perpendicular these two normals. There is no guarantee now. I need to normalize this like normal to call it a normal, because we assume the normal is the magnitude of normal is a 1 unit. So we get, this is the way we will be able to get the normal. Now, what's your name?
Ricardo.
Ricardo. So if Ricardo is like assume one of the things, which is, if we know the triangle around the point, which is very easy, if we know all these triangles, and then we can compute the normal of the first, second, and then we can sum these triangles and then normalize the final triangle, which is pretty much like the averaging, and you will get the normal of this point. Now, if we know which 2 points will give us the presumable triangle, that's fine. So we know if we get, this is the point we are like interested to compute the normal. We take these 2 points, and then we assume this is a triangle, compute it normal. We take this point, this is triangle, compute. Now, since we have a point, And if we're talking about depth image, is easy, because we pretty much could take the image, we have the structure from the image. If we talking about point cloud in general, and we don't have the structure of the image, that's tough, because we don't know approximately if this is the point, the 2 points will be one here and one here, or one here and one here. So that we need to be careful about how to pick the points that pretty much will be 2 points that will create a triangle with our point P. But if we are in a depth image, our life is much simpler. Could anyone tell me why?
You can just choose adjacent pixels.
Yes, the adjacent pixels, because pretty much we have a grid like the depth image. So if we have this point and we have this point, so we can take the neighboring point, and we know that these, at least one of the things which is, if like the best case, if this will be, these points are pretty much in a plane which is perpendicular to the camera, we'll get very accurate normal. If this plane, which is pretty much kind of like almost perpendicular to the camera, not parallel to the camera, then we will get like these points will be far away, and then we'll get like at least kind of a accuracy, like a estimation of this. So for depth image in general, we could use this technique to be able to compute the normal based on the adjacent pixel of the depth image. So definitely that's doable if we know the depth image and the structure. If we're talking about point cloud in general, it's a tough problem. Now this is the second thing. If we talk about general, the main issue, how to determine the point, the 2 points that create a triangle with our point P. One of the approximation to take a close points, but it's not maybe, could be. What's the kind of the problem with taking a close points?
Maybe I don't have the closest point, and I get more far away. I get another vector who is calculated as the same average, but he is not representing it really. Can I show it fast? What I mean? Maybe this point would not exist. I will take this point probably.
Okay.
And if this point is much far away, I get another vector here. If this is the average. This average he is noising then.
Okay. So this is one option, which is could be. The other one, if these 2 points are very close, which is mean the angle created by these 2 points will be too small, then the normal could flip. Yes, because if this angle is small, the difference will be the same normal could be either plus or minus, which is very easy, could change its position. Because if we have 2 vectors, like here, this is a vector and this is a vector, and I make a cross product of this, the normal will be up of this bone, out. If this angle is somehow not this one, but will be this one, or very small, then the normal will be inside the bone. And this is, if this is small angle, this is could either like appear as a result of floating point kind of like calculation, or just the angle is like too small. So this point could be here or could be here. So this is like the same thing. It doesn't matter if this point, one point is here and one point is here, or if the points are here, like nearby. What really determines this problem, or what make this problematic, is the fact that the angle between these 2 vectors is small. So like picking these points is tricky, so you need to have them close but not too close, and not really along like you also the angle between them should not be kind of also too small. But you don't want points which is like, if this is the point P, we don't want point in one side and this point in the other side. We get again the same problem with the normal. So you want something which is kind of like somehow close but not too close. Again, picking this point in the general point cloud is problematic and not easy. The second problem is fitting a plane, like a plane into our set of points. Let us kind of make it if we have a set of points xi, yi, zi, usually the equation of a plane will be ax plus by plus cz equal d. This is pretty much the issue, and often we write the equation of the normal as the equation of the plane. If we have a plane P and the plane is this is normal. This is its normal n. Often we can write the equation as x, y, z equal d. Yes? So this is the normal of and this is the generic x, y, z, and this is the d, which is pretty much the normal, determine the whole information about the plane except the shift up and down. So the d will determine its kind of like position. It's up and down. And if we assume our points very easy, often we could assume the expectation of these or the mean of these point xi or all our point pi is equal 0, which is mean their average is 0. This is kind of like simplify like this computation, because if the average is 0, we can assume often this d is 0. And we will see later what we want to get this. This is why we want the expectation to be 0, or the average of the points. Now, it's like, this is kind of like, this is too much to require from a point to be, the average to be 0, or it's like all our sampling points are like, their average could be 0. In general, if you have a sample points or random points, most probably, what?
It seems unrealistic.
Yes, it's most probably the average is not 0. So this is really like, it's very, very, very rare that you will get an average 0. But we could make the average 0. How we can make the average 0?
Say a close value. Those values reached, we can say it's equal to 0.
When you try and have an equal number of points above and below the plane?
So how we can do that very easy to get the points equal to 0, the average points.
Translating them?
Yeah, translate. Where to translate them?
You compute that number and you got the constant, and then you.
What's that number?
It's the average distance from the origin.
Or what we call it. We compute the center of these points. So we can compute the center of these points, which is, let us call it kind of P, which is very simple. It's one divided, if we have n point, it's pretty much all the point pi divided by n, and we get the center of these points. Yes?
It must be the center of the plane as well, right?
It's yeah. We assume if we are lucky, the plane will like be really close to that. So this is the one of the main assumptions. And now after we compute p, we create a new set of points, which will be now for every point pi. We create a new point which will be pi. Let us call it tag, which is equal pi minus tangent. Pretty much what you said. Now we translate the points such that their center will be in the 0. And this will make the expectation simple. And that simplify our computation, because that we can assume that D is 0. But even if we don't like assume D is 0, what we need to minimize, we need to, this is the equation of the plane. So if we assign, this is, we could write it as Z equal AX plus BY plus plus C, which is not, look, these are not the same ABC. This is the C should be capital, so pretty much not the same ABC. Then we can now, one of the difference, which is we see if we assign this point to this plan, we will not get it. If it's 0, it will be here, but it's not 0, could be fitted here. So what we need to minimize the square, the sum of the square difference. So the point, which is the Z value, which is this, in this case will be this one, minus the actual Z value of this point. So this is, if we assign, this is the equation of the plane there. If we assign the point, we'll get a point which is here. But this is not the actual point. This is the actual point. So pretty much we can subtract the Z value from this to get the distance over the Z axis. Just make it simple. We could actually compute the distance between a point, but for all points, and then it's also possible, but this is much simpler. Then we take this distance. Now we want to minimize this value, E of ABC. This is the variable of this equation now. But this can function in non-negative, and this is hyperbolic graph. We know that it should take its minimum when the gradient becomes 0. And so the gradient, if we take this is the gradient, and this is the point, the vector of the point, pretty much we can compute the gradient to be 0. Oh, okay, this is the gradient, pretty much differentiating the point. And then we can write this as a matrix form, which is pretty much a linear equation that could be easily solved. Actually, 3 equations that we can solve and get ABC. So it could be solved analytically very easy. And it could also, you can just plug it in a cell solver and get ABC. And that will determine, the moment you get ABC, you determine the plane. And if you determine the plane, pretty much you know the normal from the plane equation. So if I have the plane equation 5x plus 2y plus 3z equal 2, this is the normal. So what I need to get 5, 2, 3, this is the normal. What I need to normalize it. Is that clear? So this technique is pretty much also easy to do. It's much more accurate than the previous one. The previous one is quite like hard to get it right. It's simple, but I won't recommend using the first approach in kind of computing the normal of a point. Now, the third technique is based on computing the eigenvalues and eigenvectors. So I'm just kind of like let you kind of refresh your memories. If I have a matrix A and multiplied by vector x, I want this to be scalar multiplied by the vector x. So this is the matrix we going or thinking to solve. If we solve this equation, we get kind of like variables, which is this is our scalars lambda 0, lambda 1, and lambda n, which is n. If we assume this is n by n matrix, and this is vector of size n, we get n variables. if we plug every lambda here instead of this lambda, we will get a vectors v0, v1, under vn independent vectors. And these could call the eigenvalues. These are called the eigenvectors. Now, one of the approach to solve this is to try to taking kind of creating a triangular matrix. And the moment we create triangular matrix, it's very easy to compute the eigenvectors. Now, what's nice about this is that at least when they teach us algebra in the first year in computer science, you don't really what kind of why the eigenvalues and eigenvectors are so important. And at least pretty much when I learned this, I did not really kind of perceive why they are important. But they are, it's if we think about this, it's not only create kind of very its relation to transformation, it's also have a good relation to classification and the creating kind of determine the distribution of a given point set. So if we have a point set in the 2D plane, yes.
Do they have a meaning in kind of geometrically meaning?
Yes, this is exactly what I'm. These vectors are orthogonal. So what's the geometric meaning? This is exactly the point which is it's important for us. If we have a set of points, this is what we have these point cloud, and if we think about what really the meaning of the eigenvectors and the eigenvalues there. So if we compute the eigenvector, one of them will be this one in 2D, and the other one will be this one. They are perpendicular. How we know which one is this, which is the longer vector, and this is the smaller vector? These eigenvalues are it's very important, their value. So if we have, usually we order them in a way based on their value. We usually order them that lambda 0 bigger or equal to lambda 1, bigger or equal to lambda 2, and bigger or equal to lambda n minus 1, sorry. This should be minus 1. Now, which is mean that these are the vector which is more important. Now, it's useful in a lot of problems in classification and data set. If you have a data set of very large domain, let us see, your vectors are of size 1,000. All your points are in a domain 100 or 1,000. And then you want to create what we call actually often dimension reduction. You want to take them to a lower domain. You take them, for example, 10, to domain 10. Which domain you will take? Which domain you will take? One option, you want a domain that will give you the better classification of your points, yes? So this is one of the things. So the bigger the lambda, the eigenvalue, the bigger the distribution of the points along that axis. So pretty much what this simple equation, algebraic equation, take our points and convert them into different domain while actually intensifying some properties. So instead of this xy, we move to a different axis or different coordinate system. But the new coordinate system have very nice property. This vector, which will be the eigenvalues v0, which is correspondence to the eigenvector v0, which is correspondence to the eigenvalue lambda 0, will be the biggest one, will be correspondence to the first, like this long dimension, which is mean along this vector we have the largest distribution of points. If we are going to distribute the points along, like if I'm going to project these points like on this vector, I'll get the largest distribution. Is that clear? The second one will give me the second distribution, and so on. So pretty much if you want to spread your point for classification, you want to get the first 10 eigenvalues, create a new coordinate system using the first 10 eigenvectors, and then project your points into the new domain. Now, this is in 2D, and it's very simple to compute this, to also create this from like the set of points. So if we are interested, if this will be the points in the 2D plane, and I want to be the best fitting of the line here, my line will be parallel to this vector. Yes? My line will be parallel to this vector. Now, one of the things which is, since we are talking about vector, again, we need like to assume the expectation of the average of our point is 0, and then this vector will be passing through this point or through 0 or close to this point. Yes? So again, we use the same technique, which is in order to create these points. And this is pretty much what we are doing. So we'll get, this is our, like, the getting set of points. We can, here just I'm running through a very simple example. So we get kind of like compute the average. This is x bar, y bar. In this case, I will get xi, like x bar equal 12 and y bar equal 36. And then I create, which is, I call it mu, this vector, this point, which is, this is the point mu, which is the mean. And then I subtract from every point, create a new matrix, which is this matrix will be 3 by n, or 3 by 17 in this case, will be p0 minus mu, p1 minus mu, till p16 minus mu. Let's create the matrix A. Now, one of the important things, we are not interested in the kind of computing the distribution of the points, but we are interested in computing the distribution of the relation between the points, or the correlation between these points, the relation of these points. This is why we don't look into the matrix A, but we create a new matrix, which is called the covariance. The covariance is a very simple matrix, which is, it's determined the relation between the points, every pair of points along this in our data set. And this is pretty much what gives us, it's very simple to compute. We multiply A by A transpose. And this is give us 2 by 2 matrix. Why? Because this matrix was 2 by 17. And this is, if we transpose it, it will be 17 by 2, or like 17 by 2 and 2 by 17. And then we multiply these two matrices and get 2 by 2. This is very simple. Is this clear? Now we create a new matrix Q, and we're looking for Q multiplied by xy, because we are talking this example in 2D. In 3D, it will be pretty much very simple, but will give us a matrix 3 by 3. This is, in 2D, we can just really very easy solve this. So we get Q multiplied xy equal lambda multiplied by the vector xy. And then what we will get, we will take this is to be equal to 0. This is just like what we do. We multiply this is by a unit vector, move it to the other side, a unit matrix, and this is what we will get. This is simple matrix. We can solve this by eventually what this is will give us two equations that easy to solve, and we'll get lambda 0 and lambda 1, and lambda 0 will give us the vector E0, and lambda 1 will give us the vector E1. Will be the vector. This will be the biggest, the vector which is correspondence to the largest eigenvalue, and this will be correspondent to the second eigenvalue. In 3D, we'll get three vectors. One will be like to the long distribution. And if we are talking in general in point cloud, what we will get two vectors which are almost the same or very close. And then we will get smaller vector, because if we assume our point are a sample of a surface, pretty much along this like direction will give this direction the same almost, and this direction the same. But the third one, which will be the smallest one, it will be the normal of the surface at this point. Is that clear? So we'll get in this case, if we want to compute the normal of the point, it's the smallest, like the vector which is corresponding to this, to correspond to the smallest eigenvalue. Is that clear? Any question?
The smallest one?
Let us talk about 2D. 2D, if I have this surface and I want to compute the normal. Now, let us take the density of these points. Let us take this area and zoom in. So this is what we will get. So we will get one will be this. Will be the largest. Yes, will be the smallest, which is the normal. In surface, we will get if this is the surface, we'll get points. So we will have pretty much, since the distribution of the points, we'll get this vector and this vector pretty much similar in dimension. And then we will get this one, which is perpendicular to this, will be small. The nice property of these eigenvectors, they are all perpendicular to each other. No one of them could be created as linear interpolation of any other set or subset. And they are independent. This is what they are independent of each other.
Would it be possible that instead of Q, the covariance, take another matrix that also explains the relation between points that give the same results?
Okay, so let us try to get this as things. Is that clear? Let us think about this. Usually, how we compute, if we have a set of points, x0, x1, xn. In statistics, there is two basic things which are very important. What they are? Mean and variance. How we compute the mean? Mu.
Average?
It's the average. It's actually sigma for all I, xi, divided by n. Yes? How we compute the variance?
Difference to the mean.
It's difference. It's difference to so the xi minus mu. Yes? Squared. And this is give us this is the variance. We can, yeah, we can normalize. This is the variance. Now, if you think about the variance, we could, if you think about it, this is 1 divided by n sigma. Let us just write it xi minus mu multiplied by xi minus mu. Yes? This is called a variance. Now, why it's a variance? Because it's the difference, the relation, internal relation between a point and itself. This is what we call a variance. Now, a covariance, which is the covariance, if you think about this, is it's between 2 points, x and y, or like if I want to compute the covariance between point xi and xj, which is pretty much the same, but instead of computing the point we compute between xi and xi, we compute the point xi and xj. This is what's called the covariance, which is pretty much what we get from this relation. So the covariance will be between any 2 points. This is xi and xj will give us a matrix. This is what we call the covariance matrix. So the covariance, because we get the covariance between what we will get xi versus all the other. And this is will get us like one value, and this is then will get xj like and xk and so on. This is what we call the covariance. So the idea of which is, if we think about this, this is give you the relation between the points with respect to the mean. The covariance aims to give you like a relation between all the points, which is pretty much what you will get. You will get a point which determine the relation between these vectors. This is what we call the covariance matrix.
So do you think you could calculate the mean from that covariance matrix?
It's much simpler to compute the mean directly. Why you need the covariance matrix to compute it?
I'm just wondering what the covariance matrix looks like.
The covariance matrix look like? It doesn't give you much information about the mean because it's already a lot of information hidden there. It's very hard to recover the mean from the this is because what you will get if you take these points and many point sets which is have the like eventually it's you took the mean out of this kind of set of points because you assume the mean is 0. So all the points you compute the covariance matrix, you assume the mean is 0. So pretty much the mean is hidden. The mean of this is you kind of like the hidden assumption within the covariance matrix is that the mean is 0, which is mean you lost the original mean. Is that clear? So you cannot really recover the mean from this. Questions?
Why you say that the mean is 0 and the covariance item?
Again?
Why you say that you assume that the mean is 0 and the covariance?
In the beginning, what we have done, we say, okay, in order to, we want kind of like to get one of the issues, we want the points, the expectation of the points to be 0. Why we want the expectation of the points to be 0? Because we assume we want to take into account that the center of mass of our point is 0, and what we will remain to compute is the direction of the distribution. Now, in general data set, we don't have this requirement. The center of mass is usually not in 0. One option is to take our point set and translate it such that the mean will be 0. How we do that? It's very simple. We compute the mean of this, like of these points. We'll get like here, what we get the mean here. So the simple solution will be now to translate all these points by this vector, which is one could do this by taking like all the points pi and subtracting the mean from them. This is pretty much translation. So now we know that the center of mass is in 0. Now after we compute the center of mass 0, the vectors will be pretty much evaluated, because if you think we are thinking about vectors, every point we'll think about it as a vector. The difference between like the vector is always, which is from the points to from 0, the origin to this point. Now we want to take the relation between these points. So the covariance matrix, practically what it's doing, it's taking points, pair of points, which is pairs, which is in this case points, and determine the relation between the vectors representing these matrices, these points. Now, this is what will give us the covariance matrix. It's pretty much the correlation of these points. And then, now, will give us this information about the correlation. It means the distribution of these points. So this is one thing which is, originally this came from like the word of like a classification. And if you want to classify the points, let us assume this is your like a, okay, let me. Why you need that? If this is your data set, and let's assume in the 2 domain, and your points are this set and this set. You have done some experiment and get these set of points. Pretty much you get them like this. Now, one of the things which is these points, if you project them in this, you don't know really if these are, you will see pretty much the same distribution here. Yes? And you say, okay, what kind of these data, what really this thing is very important that classify my data set into 2 classes. So what dimension that's important? Let's assume things like you see, you have a lot of data, and one of the axes will be, like, for example, in your data set, one will be the gender, for example. And will be the axis of these points. And now, one of these things which is what you realize that there is a clear classification of these points based on gender. But when you look at your data set in 10 dimension, you don't see it. So if you compute now the covariance matrix and the eigenvector, you will get this vector, the biggest one, which is mean this is the one which will distribute your points. This will be your eigen, like the vector which is the largest, correspond to the largest eigenvalue. Now, one thing which is when you project them to this x and y, you will not be able to classify them into classes and say, oh, gender is the most important things. But if you think about now, this is the new coordinate system, and you project them here, you will get 1 point class here and 1 class here. And now you can separate them very easy and see this is 1 class and this is another class. Here you cannot really separate them in this. So this is where originally why we're looking for a different coordinate system that will expose, will just make things are kind of clear to differentiate between groups along this axis. So what we assume in this, that the larger the distribution, the more it will be kind of will expose the better property of classes, of different classes of the data set. So this is often called as the classification. It's one of the main technique which is used. Actually, there's often they called PCA. This is the name that you will see it, PCA, Principal Component Analysis. So the principal component analysis, there is even solvers, which is will you give it very large matrix and will give you these kind of like main vectors, or like will give you the eigenvalues and the eigenvectors. So this is something which is we use here, and it's pretty much very, very kind of useful technique because it's simple, it's algebraically robust, and it's used quite often in classification. So this is why we need this relation, because we need the relation between the various points. This is what the covariance encodes. The covariance encode the correlation between each pair of points. Okay? Is that clear? Any other question?
So you do this kind of principal component analysis for
Yeah. The neighborhood,
for
yeah.
the neighborhood. So it would be like doing these computations for
Exactly.
8 points,
Maybe 8, 10 points, depends. And this is, you will take like
and you move to the
next
one.
one and compute this, yeah. So it's, computing the normal is definitely is not cheap, but it's not kind of like hard problem, because pretty much all these are linear or quadratic at the most.
Does it makes any difference the size of the samples? I mean, because it's very small set, like 8 points.
Yeah, 8 point is maybe too small because you will not get robust. Usually, this is the minimum you want to take. So you want to take larger, like larger point, and this is definitely, but not too large. So this is, it's not really clear with this is kind of the golden value. It's not known. If you take more points, you will get more noise. If you also take too small, you get noise. This is one things that it's not easy to determine. Questions? Okay, so now what we will have after this point, let us look at some kind of one of the tricks people use for depth images, even without computing the normal. Stereo image, like stereo projection, we all like use or all know, but we project one scene to the right image, one scene to the left image, and this will be the two scenes that we kind of like interleave between them. Yes? Now, one of the nice technique is actually rendering in the frame buffer will create a depth image, because we can read the depth buffer, and that will give us the depth image of this rendered like scene. Yes? And then what we can do, we pretty much can like warp it a little bit to the left, warp it a little bit to the right to create two images, because we have information about the depth. We also kind of like a little bit maybe twist and cheat a little bit, and this is will be able to get from one image two different images. Nowadays, this is pretty much because of the speed of rendering. It's not really useful, but was a technique which is maybe useful at the time, which was like the rendering was not as fast as today. But today's the reading the depth buffer is not really fast as we think. It's going faster, but this is one of the limits. This is just to give you that this information already there in the depth buffer. You can use it. It's depth image for almost everything. It doesn't have a normal. Can anyone tell me why there is no normal in the depth images in the depth buffer? Just kind of like a.
Why would we need it?
It's actually not there because of a reason is not there, because what we use in most of in almost hardware, we used Gouraud shading and not Phong shading. So pretty much the normal is interpolated as an intensity and interpreted as an intensity and then interpolated. If we will use a Phong shading, we'll have a normal with each pixel, which is we use to compute illumination. But it's not. In the hardware, they compute the illumination for the vertices and use the interpolation. So pretty much in the depth image, and this frame buffer, it's light and it's fast because we don't use Phong shading. So every technique has advantage and disadvantage. It's because Phong shading, is that clear? Anyone want me to explain this, or is that clear?
So this is like the difference between vertex lighting and pixel lighting? I mean, like normals by pixel or normals by vertex?
Yeah, let just kind of refresh your memories. When we usually, if we have this is let's assume we have 2 points, and we have a normal here, and we have a normal here. And in smooth shading, we assume the surface is going like this. This is about smooth shading, yes? Now, if we, there was 2 techniques to compute the shading at these points, the illumination. One technique, which is called the Gouraud shading. Gouraud shading says like this: compute the illumination, which is pretty much how you will change the color of this point based on the normal and the direction of the light. This shading parameters you store here. That's it. Then you forget about these normals, and now to compute the shading here, you interpolate this shading value here and this, or shading factor here, as a linear interpolation or bilinear interpolation. This is the Gouraud shading. The Phong shading, what it's tried to do, keep the normal here, and if you have the normal, now you can compute the normal in this point as an interpolation. So you get a new normal Ni here. Now you have a lighting direction, and then you compute the shading here. But since this technology is fast, this is fast and less accurate. This is accurate. Now, this is not implemented in any hardware as far as I know. All the people are implemented is this, using kind of like light maps, all these techniques. This is, which is in the depth image, here are stored not the normal, but the shading factor. So we cannot recover the normal there. Okay? Now let's go for now we'll go we'll go for 2 hours, I said, so we'll go continuously till another I think 5-10 minutes at most, which is just we get the point that we can break and continue the next lecture. Okay? So what we will have, if we think about depth images from our perspective is a 3D. It's actually lives, depth images live in the 3D domain, which is all the geometric transformation will be in the 3D domain. Since we are assuming homogeneous coordinating system, will give us very simple 4 transformations. So this will be the translate matrix, so which is very simple. You have translation. This will be eventually subtracting the vector tx, ty from every point, or adding it in this case. And this is the scale. Sx, Sy is the scale factor. So this is pretty much we can transform every point in the depth image exactly as we transform in a point in the 3D domain. Now, contrary to images, rotation is not along a point in the 3D. It's along an axis, yes? So if it's along an axis, then we have a simple rotation along a x, simple rotation along y, and rotation along z. So we have rotation along the principal axis, which is, this is the rotation matrices, which are very simple. Now, it's often we don't want to rotate point along the principal axis, because it's often the case that we want to return about arbitrary axis, yes? Any axis A, I have any axis A, I want a point P to be rotated along this axis by an angle alpha, for example. How will do that? This is the x, y, and this is z axis. This is the system. This is
maybe a transformation of that vector to one of the axes, then rotate about their axis and move backward to the
exactly. So this is what we will. This is A. And this is our data set like along A. We create the transformation that will make this axis align, like this rotation axis A, align with one of the principal axes. That's very easy to do, which is apply this transformation to all our point, rotate around this x, and then return compute. So this will have this transformation, which will take this to align here. Let us call it T. So what we apply T in all point, which is like this is point x, I, y, I, z, I. In this, we apply a point T to the point x, I, y, I, z, I. And after we get this, we apply the rotation of angle alpha around x, and then we return T minus 1. That's simple, yes? However, computing T is not complicated mathematically, but when you come to program it, because it depends if this A is here and you want to bring it to X. It's not like you want to bring A to the closest axis in order not to kind of, after that, to try to think about changing the sign of the rotation and computing the inverse of the rotation and what's the direction of the rotation will be before or after. And there is a simple technique not to do that, just to do it directly. Do you heard about quaternion? Did you hear, like, do you know quaternion? Yeah? So use it all the time. This is pretty much the same. So what you do, you create quaternion, which is like this, which is, you will call it as an A. This will be the vector. And the scalar will be, the scalar will be cosinus 2, something like this.
I can tell you if you want.
Yeah.
You should go from a vector to a quaternion.
Yeah, it's A, and then you get the quaternion. And then you take this quaternion to rotation matrix. That's it. You are getting a rotation matrix, which will give you, I think there is something.
Angle divided by turn. The first term is sine angle divided by turn.
This A multiplied by sine. Yes,
Right,
yes,
x
yes.
times sine.
A sine alpha divided by 2 and cosinus alpha divided by 2. Okay. So this is, And then there is a pretty much very simple technique to take a quaternion, convert it into rotation matrix, and that will give you the answer. I assume everyone knows like quaternion, and you use it. Anyone like doesn't know and want kind of like to? I can talk about this the next time. Okay, so next time I'll talk about a interpolation of point cloud, and then we will see what other topic we will cover, and then we will talk about like more correspondence and images and a multi-view geometry. Okay? Okay, thank you, and see you next week.